Good morning everyone. I'm here to report the single phase AC power analysis. Power analysis is mainly classified into three types. One is apparent power, is the product of root mean square value of voltage and current. This power is measured in kilovolt ampere, kVA or MVA. It is represented by the symbol S and their SI unit is volt amp. Second, active or real power is the power which is actually consumed or utilized in an AC circuit. It is measured in kilowatt, kW or MW. It is the actual outcomes of the electrical system which runs the electric circuits of load. And the third one is the reactive power. The power which flows back and forth, that means it moves in both the direction in the circuit react upon itself. It is measured in kilovolt ampere reactive kVAR or MVAR, the power developed in the circuit reactance. This diagram here is what we call the power triangle. This triangle, we can also identify the three types of power in an AC power. First, in the hypotenuse side, where is the apparent power, is S is equal to VI is equal to square root of P squared plus Q squared. As you can see, the formula is just like a Pythagorean theorem by finding the hypotenuse. And in the opposite side, where the reactive power, Q is equal to I squared X or equal V I sine theta. And in the adjacent side is the real power, where P is equal to I squared times R is equal to VI cos theta. And this theta here is the phase angle or the power factor angle. To get the power factor is equal to cos theta or the ratio of the real power and the apparent power. A wound coil that has an inductance of 180 mH and a resistance of 35 ohms is connected to 100 volts and 50 Hz supply. Calculate A. The impedance of the coil, B. The current, C. The power factor, D. The apparent power consumed. And now, let's calculate the impedance of the coil. Given R is equal to 35 ohms and L, which is the inductance, is equal to 180 mH and V is equal to 100 volts and F, which is frequency, is equal to 50 Hz. We know that the formula of Z, which is the impedance of the coil, is square root of R squared plus XL squared. And to get the impedance of the coil, simply substitute the value of R, which is 35. But we don't have the value of XL, and we need to solve it. We know that XL is equal to 2 pi FL, and we can get the value of XL by substituting the value of frequency, which is 50 Hz, and the value of inductance, which is 180 times 10 to the power of -3, and we can get the value of XL, which is 56.6 ohms, and to and we can now get the value of impedance of the coil, which is the square root of 35 squared plus the value of XL, 56.6 squared, and we can now get the 66.5 ohms, which is the value of impedance of the coil. And now we will be solving the current I consumed by the coil. We know that the formula of volts is I times Z, which is the impedance of resistance, and we can get that I is equal to V over Z, which is we have the value of volts, which is 100, and the Z that we solved lately is equal to 66.5, and we now have the current, which is 1.5 amperes. And now we will be solving for our power factor and phase angle theta. Given resistance is 35, we know that the power factor is equal to cosine theta, which is equal to R over Z. Because in the impedance triangle, R is in the adjacent side and Z is in the opposite side. And to get the power factor, we can simply substitute the value of R, which is 35, and Z that we solved lately, it is 66.5, which is equal to 0.5263, which is our power factor. And for finding the phase angle theta, simply we know that angle theta is equal to R cos, then simply use the value of power factor, which is 0.5263, and we now have 58.2 degree, which is our phase angle. And now we will be solving for our apparent power S consumed by the coil. We know that the formula of apparent power is S equals V times I, and we know that we already have the value of volts, which is 100 times 1.5, which is the value of current that we solved lately. And now we have the apparent power value, 150 volt ampere. I have another sample of finding the real or active power and reactive power. An AC circuit load is rated 160 kVA at a lagging power factor of 0.75. Determine real and reactive powers. In example number 2, we were asked to find the real or active power and reactive power. Using ka in Sokatoa, we know that ka is cosine is equal P over S, which is in the power triangle P is in the adjacent side and S is in the hypotenuse side. We can now identify of P, which is P is equal to S cosine theta. But we only have the value of S, which is the apparent power, 160 kVA. Then we need to solve the value of phase angle in cosine theta. To get the phase angle, we have theta is equal to r cos 0.75, which is the lagging power factor. And it is equal to 41, and we can get 41.41 degree, which is our phase angle. And we can now solve for the real or active power, which is S, or the apparent power, is equal to 160 kVA, and cosine theta is equal to cos 41.41 degree is equal to 120 kilowatts, which is our real or active power. And now we will be finding for our reactive power, and we will be using and Sokatoa, which is sine theta is equal to Q over S, where in the power triangle Q is in the opposite side and S is in the opposite hypotenuse side. And in this formula, we can identify the Q is equal S sine theta, and we simply substitute the value of S cos 160 kVA and sine, which is the phase angle, has the value that we solved lately, which is the 41.41 degree, and it is now equal to 105.83 kVR, or kilovolts ampere reactive. The difference between active and passive components. Active components are those who delivers or produce energy or power in the form of a voltage or current. Passive components are those who utilizes or store energy in the form of voltage or current. Next is examples of the active components are diodes, transistors, CR, integrated circuits, etc. Similarly, examples of the passive components are resistor, capacitor, and inductor. Next is the active components are capable of providing the power gain, whereas the passive components are not capable of providing the power gain. And next is active components can control the flow of current, but the passive components cannot control the flow of the current. Last is the active components are energy donor, whereas the passive components are energy acceptor.